that we have to keep in our mind. So beta n is the reflection amplitude, theta n is 0 to 2 pi phase shift, and there are n number of elements, and the received signal y of n, not the received signal, the reflected signal from the nth IRS element is this. Okay, this is the step 1. We need to understand it. Okay, there are papers who will give you what set of betas and thetas you need to choose. Okay, this will be discrete phase shift versus continuous phase shift and so on. So for our purpose to serve, we first studied, again I will come back to the same model, that no source and destination, there is a block and you have IRS element. And once you understand this, generalization to multiple setups are possible. Once you have multiple antennas at the S, there will be a different problem. Once you have multiple antenna at destination, you will have a different problem. Okay, so let's start with SISO system. And we have studied that if you do not have a direct source to destination link, then what is your received signal is this. Okay, so this expression is quite general in the sense, if you look at carefully, you have a PLR, square root of PLR. So this expression is valid for both the frequency MM wave versus the below MM wave or normal 6 GHz, below 6 GHz range. You just have to worry about what is my suitable path loss model I need to put here to go ahead with the analysis. Okay, now this already we have covered. I am going fast a little bit here. So the goal is once you have your received signal at the destination from the IRS reflected reflected link, then our goal will be to maximize the SNR. Okay, that is very easy to see. And the condition that will maximize is delta phi I has to be equal to 0, and you adjust your phases accordingly to get the maximum benefit for the destination. Okay, so this is the very simple layman approach of looking what is your optimal phases. Okay, now this is a simple scenario, and the importance of understanding the optimal phases will take you go ahead if you dump one top of another, multiple antennas at base stations, what will be your optimal phase? Or if you talk about a different system model for cognitive radio, you will get a different answer. Okay, but what is the main objective? You have to maximize your SNR, which will be minimizing the error probability or outage probability. But also keep into mind that I will be having some more constraints depending on the different setups. So this is my case 1. The case 2 is if you have a direct source to destination link. For example, if you have a strong SD link, then you see if I have to move forward, I need to write first the received signal, find the SNR, and same the third is how do you choose your phi I to maximize the SNR at the destination. Okay, so way forward we have to deal with a lot of mathematics and complex notations. We should not be worried about all these things, but the major things is just to compact notations. We use some matrix based notational here. So if you talk about your channel from S to IRS is AHR, we can talk about a n cross 1 channel or 1 cross n channel, and this is your G, and this is a theta matrix here. And the matrix theta is a diagonal matrix. So what is exactly theta? That is a diagonal matrix where the diagonal elements are given by the IRS absorption coefficient and the reflection beta into e to the power j theta. Okay, people will assume all beta I to beta n1 for simplicity. But let's say if you do not assume this, if you keep betas also here, and you want to write your model in a quite a general format. So this is the way actually we should write. Y of t is HR Hermitian, theta G, this is a matrix we call, this is a cascaded channel via IRS. Okay, so we have two channels. One is the line of sight channel when there is a with a direct SD link, and another is the cascaded channel via the IRS. Okay, and the destination will see the two together. Okay, what it will do under these two channels, the job is to add these two signal. Okay, so Y will be the summation of two channel. One is the cascaded channel, which is this I can see, this is my cascaded channel, and HD star is the direct channel. Okay, so why star? That's because I am just copying the notations from the paper itself. But if you do not like star, you can well assume HD for your direct link and do the analysis accordingly. Okay, so basically there is one channel HD, and there is a vector here, there is a matrix here, and there is a vector here. They will form a cascaded channel. They will add up, and I will get my received signal with, this is my signal strength, and this is the AWGN noise. All right. So now the next step is same, that we want to maximize the SNR. So you need to know how to compute the SNR, and the SNR is nothing but signal powered by noise power. You have just additional term here, and you can simply write this term here. Okay, now we focus on maximizing the rate. Okay, this is just for looking into whether you want to maximize the rate. That in turn implies you have to maximize the received SNR. Okay, so maximizing the rate is nothing but maximizing the received SNR. Maximizing the received SNR is something like this form. Okay, where I can see this amplitude will have a phase term here, and HRN and GN will also have amplitude and phase, and HD star will also have amplitude and phase. Okay, so this, if you incorporate all things together, we can have a optimization problem. Right, so let's maximize the numerator, which is my SNR term numerator, mod square, which is the SNR in number of elements. You are maximizing over theta. What is this theta? This maximizing over theta will come from here. So you can see you have to optimize the reflection coefficient theta 1 to theta n. That's why they have make a vector theta 1 to theta n, and also they have make a beta vector, which is the beta 1 to beta n. Okay, now they started writing the maximization problem over both the variables theta and beta, putting the constraint theta is a phase 0 to 2 pi, beta is a absorption coefficient, it's between 0 and 1. Okay, now they come up with the optimal phase shift for a given beta. Okay, and this answer is proven in that paper to be this. Okay, so basically I am not going to prove this answer, but you have to go back and see why the theta n star is mod of zeta minus theta n plus psi n. So what is this phi n? Phi n, so remember what is theta? Theta is the IRS phase shift for the nth element. Phi is the first of link S to IRS, and psi in the IRS to D link. And zeta is the phase of the, these are all the phase term, phase of the direct source to D link. And if you are exceeding the mod of this comma 2 pi. Okay, so this is the way we have to understand. Go back and try to prove this. If you have this, try to prove this. Okay, but the intention is clear. So what is my intention? This is I have to maximize the SNR at the destination, and I have two paths. One is S to D, another is the cascaded path. So my phase elements theta n will be adjusted such that both the two signals will do a coherent combining and maximize the SNR. And the coherent combining approach is achieved by this. Okay. So, and also they have claimed that this optimal phase is independent of beta. Okay. So regardless of their absorption, whether it is absorbing or not, my phase element, my element of theta n star, the optimal value is only depending on SD channel phase, that's phase of the source to IRS and IRS to D. Okay, for nth element. Do for different element, you have to adjust differently. For this simple SISO model with a direct link. So this model will be applicable when you are talking about a no indoor kind of setup. You have a single input, single antenna source and single antenna receiver, and you place an IRS on the wall of the room. And how do you adjust the phases? This paper will try to give your answer. Okay, and really, if you are interested in hardware implementations, you have to see if I adjust this phase accordingly, am I getting the signal, good signal strength reflected from the IRS? Okay, if you off the IRS and if you on the IRS, whether I am getting a good improvement or not. Okay, this is the way we should look at. Now, so this is a tutorial paper, and this proof of this particular problem is one reference of the tutorial paper. So the tutorial paper, if you are interested, you have to go through all these pages, and they refer this paper where this is proven. You can go back and check. Now, with these two simple cases, I will not go into other complicated problems. One, due to the interest of time. Second, due to the it will take a lot of good mathematics and complex analysis to do, which might not be the good intention for today. So this is your job to understand different directions of reflection optimization tools. Okay, so for example, if you want to have multiple input base station, then you have to do a joint active beamforming of AP and passive beamforming of IRS. Okay, so you can see the paper, which is this one, via joint active and passive beamforming. Next, people are also interested in NOMA. Now, in non-orthogonal multiple access, which is a NOMA principle, if you fit your IRS, the problem will be different. So you have to worry about how do I serve these multiple users. With the point you have to keep in your mind, I have to do interference cancellation and technique for IRS. And also you have to talk about how do I maximize the rate or throughput for all the users. So you will have to deal with a different reflection optimization problem with some constraint. Then multi-user MIMO, there also you might have to deal with some different setup. Okay, these are all different angles. Okay, and it will take some time to understand the topic and really do a research. Okay, but people are already quite actively investigating all these scenarios. So what will be the change if you talk about your narrow band fading versus wide band fading, your frequency selective fading? Then when you do not have your perfect channel state information, which is very crucial to get these IRS reflection coefficient optimizations. If you do not have this your zeta or theta value, you cannot do you cannot maximize your SNR. What you will end up of having some underestimate, like your SNR will be less, and that's your impact of imperfect CSI. So some people already have a good understanding that what's the impact of imperfect CSI. Your CSI is not accurate versus partial CSI versus statistical CSI. So these are all different directions, the impact on performance. Okay, other related applications as usual. Now, with this going to the design challenge 2. Now, the next couple of things that we have to deal with is the placement of IRS deployment. Okay, so this is another stage. So now, what we can see, this is very simple. Why I put it in the slide? Because even I only get to understand this concept. I just took this concept, which are very, very simple to understand and very, very simple to teach others. And you see this, this is quite intuitive. So what is happening here? The question we are asking the following: you have a AP, you have a user, and you have a direct link. It might be there, might not be there. There might be obstacle, which is shown here. And the distance between AP and the users is capital D. Okay, now your IRS friend is here, and you want to ask the question where shall I place the IRS? Okay, shall I place the IRS here or here or here or here? I do not know. I know I have a distance, AP and user, the direct link might be blocked, and IRS is there. Your question is where to place. That is the questions when you go and set up an indoor environment. The first question you will be asking yourself, where should I place it? To get the answer, we have to know mathematics. Okay? Without mathematics, engineering is incomplete. So now we have to answer, how do you approach? So let me make another variable, that the placement of IRS from the AP or from the user, you make some assumption. So in this particular picture, it is going for user to AP. So they have taken another variable, which is small d. Small d is the distance between user and IRS. And they are going to tune the value parameter, and they are going to find what values of d am I getting the maximum SNR. That's the normal way people will attack. So what is your received SNR? Okay, that we have to understand this equations from the paper that I will show, and but I will not show the proof. This is your homework. You have to tell the received SNR formula is indeed this. Okay, if you cannot answer this, you are not a good candidate for IRS theoretical research. Okay, even we do not, we only accept the things without proving the things. That's very negative way of doing research. Okay, first and foremost thing, you have to ask yourself, how I get this expression. Okay, so what is happening here? I just give you some hint. So for example, there is a SNR. Where is what is the SNR? Where I am SNR is calculating at the receiver, and in this case my arrow is here. So AP, I am calculating my SNR. You are transmitting at a power P, and you are using a path loss model. For example, let's say you are using a simplified path loss model, looking the notations beta naught, which I took from the paper, and beta naught denotes the path loss at reference distance of 1 meter. So if you remember your wireless communication course, if you have studied, so your received power is transmit power times you have some constant k into some d naught by d whole to the power gamma. Okay, this is your model. Your professors will teach received power is transmit power into some constant k d naught by d whole to the power gamma. For example, gamma is 2. This is the path loss exponent. D naught is the reference distance, that is called reference distance d naught, and d is the distance between transmitter and receiver, and k is the parameter. It's a constant. It will depend on wavelength and so on. Now beta naught is nothing but it's a path loss. Now what do you mean by path loss? This is nothing but your received power divided by transmit power. Okay, this is my path loss. Received power will be obviously less than this. So PR is received power is less than transmit power. This factor will be 1. Okay, now at a reference distance, let's substitute D equal to D naught. What you will get is PR equal to PT into K. Okay, so this K parameter is beta naught here. Okay, that's how you are going to map your knowledge to the paper and you understand the math behind it. Beta naught is your K in the simplified path loss model. Okay. Okay. Once I know my parameter, I have to answer a 2-ray model and I need to find the SNR. You write your expression of Y and yeah, you have to, no, it's not 2-ray. If you discard this path, it is only like a reflected wave. So the signal is coming from here to here and here. So what is the distance that it needs to traverse is this and this. Okay, so it will see one path, which is the distance from here to here. And what is the distance? D square plus H square. So you will see one factor coming up here. And what's the distance here? Capital D minus D. This is capital D minus D. And this is my H. So you will see another distance coming up here. So hopefully we are going in the correct directions to understand this. And let's believe as of now, although this is not proven. Now you are asking the next question, how do I optimize rho as a function of, so your question will be maximum rho as a function of small d. Okay, my small d can take between 0 and capital D, because small d is the distance between user and AP, where do you place your IRS at a small distance apart. Okay, and this is high school math. You can do this. Optimize, you can derivative and respect to 0 and set it. Your optimal choice will be at D equal to 0 or D equal to capital D. So it means that you can place either the IRS here or the IRS here, which will give you the same answer, the maximum received answer, because you can see if I substitute D equal to capital D, I will get D square plus H square and small capital D square plus H square. Okay, on the other way also you will get the same answer and you will be having this factor, which is your SNR, maximum received SNR, and people are smart in doing approximation. When your D is greater H, the height, then you will have, you can neglect H here, you will have here. Okay, fine. So now let me do some justifications or understanding this equation better in a plot. So we plot the received SNR versus small d. Okay, obviously I should be having maximum SNR when d equal to 0. That meaning that when the IRS is located to the user, where is the situations here? This is the received SNR and equal to d, and in between I am getting this kind of curve which tells that it decreases, it minimizes, it increases. Okay, and we get very 0 to 500 meter is your small d. So basically your capital D is 500 meter here. Okay, they are going 500 meter range, meaning not too far, not too less. It's quite good. Okay, so we get something out of it. Okay, now people are not happy. Okay, so they want to. Okay, by the way, where is this paper? IEEE. Okay, this is the same tutorial paper. I just give the tutorial paper reference because it actually describes everything and it gives the references where you have to go accurately to get this answer. Okay, that's why a tutorial paper for the beginners will be very helpful. Okay, and also it's recent 2021. You will get a lot of good hack that reviewers are asking for to get your paper accepted. IRS deployment. Okay, IRS deployment, the second problem is whether shall I put a single IRS or double IRS? Okay, what do you mean by double IRS? Let's say I have a single IRS which is of n element. Okay, these are n element. Now I am if n is higher, I may not have the space to put that big IRS. Instead, can I break the n by 2 and n by 2, and I will place them one here and another here, and I will compare which is better. Okay, so that is my IRS, cooperative IRS. We call it the term cooperative IRS. So the major motivation is it better to utilize them as a single IRS or split into two IRSs? Okay, now again they come up with the answer when you actually split up into two, n by 2, n by 2, and place them one at, because already the answer where to place the IRS is optimal, d equal to 0 and d. Keeping into this mind, you can place them smartly and you put n by 2, n by 2, you compute the received SNR with your basic math, you get this answer. So this is, if I compare these expressions, you have earlier expression p into beta naught cube n square by h square d square sigma square. Okay, this was your earlier answer with single n element IRS. Right, now you can see I have something more, something less. What is more? You see that you have a trade-off. Now with n square, it is n to the power 4 by 16, which means n by 2 whole to the power 4. From h square d square, I went up to h to the power 4 d square. So I get a benefit here, but I get a hit here, because my h is more, h square is, and again it's a product distance, h square is coming up, so it will be reducing your SNR, but it is n to the power 4, it try to improve your SNR, so I get a trade-off. The third suitable question is, at what will be your criteria to choose scenario 1 versus scenario 2. Okay, and people got the answer that cooperative scheme is better when, so they compared this to under what situations this will be winning is when n greater than 4h by square root of beta naught. So it depends on the parameter h, which is the height of the IRS from the user, and the path loss at the reference distance. Okay, so your number of IRS element is slightly, it's higher compared to this ratio, then it will be better you split into two and use it two small IRS rather than a big IRS. Okay, now they also have plotted, okay, to give you the benefit of single IRS versus two cooperative IRSs. They have plotted received SNR versus IRS reflecting elements n. Okay, this is 1000. They've gone up to 1000. They start with somewhere around 20 or so. So what you can see, this is my single and this is my two cooperative IRSs. So you have a region where below this, my single one will win. Okay, and beyond this, when n greater than a threshold, your cooperative one will win. It will give you more received SNR compared to this, and it increases also faster with respect to number of elements in IRS. Okay, so if you are interested, cooperative double IRS aided communication, beamforming design and power scaling. Okay, very recent paper 2020. Okay. Also, one more performance result we have that received SNR versus IRS user distance. So this is just we saw for a single IRS, my curve is this. For double IRS, even I am getting more benefit here. At the d equal to 0, what you are getting with cooperative IRS, you are getting a benefit here. Okay, this is with cooperative to cooperative IRS. So this will give the engineers good insights about will it be better to put a big IRS, or it will be exploiting partitioning the IRS into two multiple cooperative IRSs for practical deployment. You can go one step further. Can you divide further? 2, can you divide 4? Divide by 4 and place them in appropriate positions such that you can even win this double cooperative IRSs. Again, the research students has to take this problem and go ahead. Okay, coming to the IRS deployment challenges. Okay, we have seen two very basic examples when we not gone too much far. Now there are challenges for large size wireless network. Okay, when you talk about deploying IRS practical network, you have to deal with large size wireless network with lot of users, their compact locations. So you have to talk about massively deployed IRS, and the problem is how to optimally deploy them such that we have to get the benefit without doing much computational task. Okay, so this is a very interesting problem. Those are interested in stochastic geometry and machine learning, for them it's a good attack. Next is the IRS deployment at the network level. Okay, those interested in doing my research from network layer point of view, looking the problem into multiple access schemes. So which is better? Will the centralized scheme is better, network level, or distributed scheme? Now, exactly what do you mean by centralized scheme? So you have a central IRS, which is only one IRS, which is located very close to your user AP base station or access point, and there are users here. Now you are talking about a centralized IRS. You are getting the one IRS only. Okay, this is the centralized versus distributed, meaning you are going to see partitioning the IRSs into, let's say your total number of IRS element is n, and your total number of IRS elements are now divided by n by k, and you place k of them. Okay, such that total number of IRS element will still remain n, but you just divide them and place suitably, meaning you just place near to the user, okay, close to the user, and let the user one pick its closest IRS to transmit to AP. Okay, this is the distributed scheme. So people also have thought about this, which is better, deploying a centralized IRS with all the elements n here, or distributing this nk by n by k n by k and putting it together such that this constraint is met. Okay, there is a paper which talk about this. I think the citation is missing here, but people are working on, if you just see the tutorial paper, the citation is there, which has come up with some kind of performance analysis, which is better centralized and distributed. Okay, now next part that we will focus on the channel estimation problem. Okay, this is also a major important topic that people has to understand if really they want to implement it. Okay, channel estimation problem. Okay, so what are the channels that is troubling us? So there is a base station user channel that is as usual. Okay, this when we talk about your 5G, you also have a base station and user channel, and that you have to estimate in order to do a lot of different performance. Why do you need channel estimations? One is base station has to do scheduling, or it has to multiple access scheme. What kind of different access schemes are there? Which users I will choose? From the user perspective, it has to do coherent combinations, maximal ratio combining. All those things will need your channel estimations. Okay, and for that, channel estimation is a inbuilt problem in wireless communications. People have using MMSE maximum likelihood based, sparse based, all these different techniques are there for channel estimations. Okay, already well developed literature. What is the extra problem for IRS edit is you have another two links apart from BS user, which is the BS IRS link, which is the base station and IRS link, which might be quasi-static because my IRS will be, no, it's not moving. It's a fixed, I have a patch, I just fix it on the wall. So base station is also fixed. This is almost a quasi-static channel, and you have a moving channel from IRS to the users. It's still varying, and you need to estimate it very carefully in real time. Okay, so this is a two extra burden that we have to think of. Major challenges. The IRS is passive. Again, the problem how a passive element can do a pilot-based channel estimation scheme. Okay, so the first thing is IRS cannot send pilot signals for channel estimation. IRS is passive element. Okay, so you have to come up with your alternate solutions. How do you estimate the IRS and base station channel and IRS and user channel? Keeping in your mind IRS is passive. It cannot transmit pilot signals. Okay, who will do that? Will base station will take the burden every time? I will send your pilot, and even if the base station will send the pilot, what about the other way around? If that link is not time division duplex. So there are a lot of problems here. Now coming to the second major challenge, large number of channels you have to estimate. Why large number? You have IRS. You are talking about putting more N will be beneficial. So your N is number of IRS element, M is number of base station antenna. So there will be M into N for the first of link, and there will be N times K users. Okay, this is for the second of link for K users. So this is the burden, that pilot estimation overhead burden will be order of this for this setup. Okay, this is not really a good amount of channel we have to deal with. And IRS performance gains is zero if we do not, zero meaning it will not be that fruitful if you do not have perfect CSI available in your hand. Okay, so what is the way around? So generally people approaches two schemes. One is semi-passive IRS. So here is a hit. We are introducing a term semi-passive. We have to carefully see what do you mean by that. And there is a fully passive IRS, which is as usual IRS. But what is the scheme you follow for these two things? So first come to semi-passive IRS. Okay, this is a big picture, need a lot of good understanding. So you see this is a base station, there is a IRS, and IRS, my IRS is now semi-passive. What do you mean by semi-passive? I have some red dots, which are sensing devices. These are some active. Okay, they are sensing devices and they are used to do pilot-based channel estimation. They are incorporated forcefully to do it at the cost of complexity, hardware, other overhead. But if I have to leverage all these IRS application advantages, I need to measure. If you have a flexibility to tolerate with complexity, you can go ahead with semi-passive IRS. What's the protocol? So this is a three-phase setup. You can see there is a link from IRS controller to IRS both way, and there is a backhaul link from IRS controller to base station. There are users. This is IRS. These are some active sensing devices. So the sensing devices are made entirely for channel estimation purpose, not for others. Reflections IRS element will do as usual. Phase 1. Base station will transmit their signal. Users will receive it, and due to the broadcast nature, the IRS will also receive. Who will receive that? My reflection coefficients will be off that time. It only the sensing elements that will be on, and they will get the signals from base stations. Pilot signal. Using the pilot signal based channel estimation scheme, they will estimate the channel of BS to IRS and also user to IRS. Okay, if it is downlink, BS to IRS, if it is uplink, user to IRS. So that's why the oblique is there. Okay, BS or user sends pilots. If user send pilots, it will estimate this channel. Which channel? Base station to IRS or user to IRS, not the other way around. Okay, because they cannot, they are not, they are only to sense the received signal, do the channel estimation. Now the channel estimation will you have estimated the channel. So the phase 2 is for information exchange. Who will do? So basically the IRS controller now will take the burden of, there is a backhaul link, IRS control link, there is a two-way link where my reflections, these channel phases will be needed, okay, to compute these phi, all phi I equal to 1 to n. These are needed because without the phi I cannot optimize the reflection coefficient to get SNR maximization. So base station and IRS need to do information exchange. Base station can do active beamforming to know once the phi I are known, it will be also used for the active beamforming purpose. The channels are also used for active beamforming purpose. Both way, right? My channels are used for beamforming, also passive beamforming here. Okay, that's why the base station also needs to know the channel. Once the channel estimation is done, phase 1 and phase 2, now the data transmission phase, where this will be off, only the IRS element will be on. And as usual, base station will transmit the data to IRS, reflect element will reflect, users will receive, and as usual. Phase 3 is the data transmission. Okay, extra burden. Now it is equipped with low-cost RF chains because it has to deal with sensing devices and need to be integrated into IRS for channel estimation. Operation mode, channel sensing, IRS estimate the CSI from the BS or from the user to IRS link. Reflect elements are off. IRS controller base station information exchange to do active and passive beamforming. After that, once you set your phase, you do active and passive beamforming, then you transmit your data. When you transmit your data, you switch off these sensing devices and switch on the reflection mode to reflection elements, and you do your transmit data. Okay, so this method has a disadvantage because it is only made for time division duplexing, where we assume the uplink channel and downlink channel are exactly same by using channel reciprocity. If you do not assume TDD for FDD case, your IRS to user will not be the same from user to IRS. It has to have two different channels, and that cannot be done by this mechanism. So if you have to talk about FDD scheme, full frequency division duplexing scheme, where the uplink and downlink channel are different, semi-passive will not work. Okay, so with this we have to go into case 2. Okay, so where we talk about fully passive IRS, this is somewhat different. Okay, so now people are well aware of channel estimation from BS to user. This is already well established frameworks are there for channel estimation. Okay, in number of possibilities, but yet it's there. And 5G also, people are using MMSE technique for channel estimation. Now there is a IRS aided channel, and I know I cannot have any active elements on IRS. So what is the best option? I can talk about a cascaded channel estimation. The cascaded channel is from user to IRS to base station. Okay, so can I, with this fully passive one, can I do some cascaded user IRS base station channels either at base station or users? Okay, so in the uplink or downlink cases. So if in the uplink user IRS base station channel is estimated in the base station maybe, and in the downlink in the user, this channel. So both way channel estimation is possible because users are active here, base station are active here. So there is no problem TDD versus FDD. But There is also question how will the cascaded channel will serve your purpose. So hopefully most of the research work that we see that no, if you also know the cascaded channel information from the perspective of this joint beamforming, it is sufficient. Okay, so people are talking about how to estimate the cascaded channel more efficiently for this case, and which is happen. You can see a lot of research going on in this direction. Okay, so again, I am citing a single paper, which is the mother of all things. You can go anywhere you want from here. Okay, now coming to this, wrap it up. Now, there are future research problems. Okay, determination of fundamental performance limits of IRS aided network. Okay, so fundamental performance limits. Okay, although I am not aware of it, you have to come up with the answer in future. Robust optimization and resource allocation issue. Okay, this is there, optimization and resource allocation in terms of space, time, and frequency. Optimal placement and optimization of the overall network. Low complex and energy efficient channel estimation protocol design. Okay, channel estimation is very crucial here. You have to talk about low complex and energy efficient. Okay, so that I should have some resources to transmit my actual data. Okay, and also people are also looking from the physics point of view to model the IRS and to incorporate the hardware impairment into it. Okay, and there will be possible extension for millimeter wave and teragigahertz where your AI ML technique can be used. Okay, so this is the right time to jump into the ocean of IRS. So with this, we just summarize our today's workshop session. So we are talking about future 6G, where we have not happy with MIMO, but people want low cost, energy efficient, spectrally efficient schemes, as a large number of devices are there, IoT set of applications. So can we have low cost schemes by using IRS? Okay, so it'll be access point, there is a IRS, there is a brick wall controller, and here, so the burden mostly will lie on the controller. How do you optimally switch your IRS phases, okay, to get the benefit out of it? Okay, so we highlighted the three major challenges: passive beamforming, deployment, and channel estimations, and there are n possibilities out of these three. Okay. So with this, there is a plenty of opportunity there in academia, and hopefully industry also, after everything will come out in 2024 and so on. Now everything is in the bucket of academia, mostly. Some of them has also started industry oriented job for IRS. Even in academia also, might be someone is working IIT, some of my friends are they are already started on kind of collaborative work to implement the IRS in their lab. Okay, it has exploration of futuristic scenarios, large number of devices. How do you tackle this EMBB scenario, URLLC scenario, even when we talk about the standardizations of IRS into different existing technologies, okay, which has to be standardized. So thank you everyone for your attention. And this is our small IRS group, started last year only in IIITB. And we want fruitful research students here to carry on IRS research.